Welcome to Lecture Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlap Observatory. Together with Shaheen Dashkian, our Outreach Coordinator, I am delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. Please take a moment to say hi in the YouTube chat and tell us where you are joining us from. This helps us to make sure that our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope. While we miss working from the DDO facility, we are happy to bring you this lecture night and this series of lectures through this webcast instead. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It's my great pleasure to introduce our speaker for tonight's lecture, Adaeze Ibik. Ms. Ibik is a PhD student at the David A. Dunlap Department of Astronomy and Astrophysics at the University of Toronto. She is from the eastern part of Nigeria in Africa and holds Bachelors and Masters degrees in physics from the University of Nigeria, Nsukka. With a passion for STEM development in Africa, Adaeze is one of the instructors for PASEA, the Pan-African School for Emerging Astronomers, which is a biannual event across Africa. She has also been involved with lots of other science outreach projects and science communication in Africa and in Canada. As a student, she spends most of her time studying the explosions in the universe, such as fast radio bursts and supernova, using different types of telescopes like CHIME. In part, her research aims to understand the universe and to create awareness of our origin as humans through science communication. Tonight, Adaze's lecture is titled The Life Cycle of Massive Stars and examines how stars grow from birth to boom. If you, our viewers, have questions for Adaeze, please ask them in the YouTube chat. She will have some time to answer questions throughout and at the end of her talk. So please join me now in welcoming Adaeze Ibik.
Hi everyone. Yeah, I'm very excited to be here to talk to you. It's a privilege, and I thank the Royal Astronomical Society of Canada and the David Dunlap Observatory for this opportunity. So, yeah, I'm going to start. And so I'm just going to give us a story. So let's not be maybe intention, because this is going to be fun. So relax as we go through, this story of a massive star. So I want us to be excited about it. All right, so let's get into it. Right, so the image you have here is showing beautiful different phases of a massive star. And so we are going to go through this today, beginning from the region where it's labeled the interstellar cloud. This is like the beginning stage, and we pass through, this journey until we get to the end of it, one after the other. So let's get into it. So the first thing I'll be talking about today is the early phases. Before any star is born, it all starts with a giant molecular cloud. So first of all, I'm sure we all, see a lot of stars. When we look up in the night sky, we see different things, and most times we think all of them are stars. So today I'm going to let you know maybe how you can identify the ones that are stars and the ones that are not. Because up there we see stars, we see planets, we see some galaxies and some other objects, and some of the things we see are some phases of stars that are, not just an ordinary star. All right, like we're going to be seeing today. So the first of it I want us to talk about is what we call the giant molecular cloud. It's also called the nebula. So for every star, they all start from a cloud. So a cloud, just as the name goes, a cloud, is made up of dust and gas. So gas of different materials and dust combined together, they could be huge, very huge and massive. And so what happens is that a lot of them gets together, and so gravity pulls them together that they begin to become dense and denser and denser. They sometimes fragment into different smaller ones, and then the different smaller ones also continue to collapse onto itself until the core becomes hot enough to ignite what will end up becoming a star. And so this process goes alongside as the planets would also form. So for every star, if it has to form planets, they all form simultaneously. So a typical cloud would form planets together with their stars and has a lot of stars forming all at once. So an example that we'll be looking at today is the Orion cloud or the Orion nebula. So I'm sure most of us already know the Orion constellation, which is very visible here in North America in the winter period. So from November to February, we are able to see Orion. So the image by the side is the Orion Nebula, that is one of the closest cloud to us. Is about 1,300 light years away from us. So when I mean light years, it's actually a distance. So the distance that it will take, a light, when I mean light, I mean a radiation or an electromagnetic light to travel from Earth to that location or from that location to us. So that distance is 1,300 years. So it will take that time to get to us. That means the way we see these things now is really, really the way they were 1,300 years ago, right? And as time goes by, we can see how they are in more present times. So if I want to see the way this cloud is today, then I need to wait in the next 1,300 years to really see that. I know that's crazy, but this is what happens in astronomy. So we look back in time while we study these things, when we study these objects, which is interesting because, we want to understand our origin, we want to understand where we're coming from, we want to know what happened in the past. So that's fascinating to know. So this is an atypical cloud, and here we could see that there are different colors of light, different stars, different things, some filaments, some of these things are what we, call the star-forming regions. So every cloud, like I said, form multiple stars at the same time. So this is a very active cloud because it's forming a lot of stars right now. And there are some popular stars that we know, that reside in this cloud even now. So we see all of those bluish ones, we see some reddish ones, and different colors of them. So we'll be learning more about these different colors in the course of the lecture. So yeah, this is the building block of stars and planets. So we see that from this cloud, a lot of stars are formed together with their planets. Now, before the star form, it has to obey some conditions that we'll be seeing later. But there is a certain condition that would allow for the core of the whatever ball that is about to become a star would have, so that the fuel, I'm calling it fuel for now, that would power the star would start burning. So that condition is that it should be dense enough for the physics that require that to happen to actually start taking place, and we call that process of burning nuclear fusion. Right. So that stage before it starts burning is what we call the protostar. So before it eventually starts burning in the core it's like a very spherical thing with disk around it, with all of the other planets. It is going to have planets depending on the mass of materials around. That's what determines whether it's going to form planets with it or not. And so that disk is what we did with the cylindrical or with the spherical thing ball that is not yet burning is what we call the protostar. So when it eventually starts burning, then it becomes a star. That's when a star is born. So now I'm going to take us a step back. Now there are different sizes of those spherical balls, and that is where I'm going to draw a line. So for today, we'll be paying attention to the very massive ones, bigger than our sun. So our sun is a medium-sized star. There are a lot of stars that are bigger than, our sun. It's a typical star, but it's not as big. So depending on the mass of this spherical ball, so the ones lower, maybe less massive than our sun, they are not massive enough, they're not big stars. So today we are not interested in things like the sun, and lower. We are interested in things that are 8 times massive than the sun. And so those kind of stars tend to shine like bluish. So they kind of give off a lot of blue light, so that when you look up the sky and you see some of those bluish things, it could be, that you are looking at a massive star. Sometimes it might not be, but most of the time, those bluish ones are massive stars. And we are going to learn why they tend to have that kind of blue light. Okay, so let's just look at some of the important details. So like I said before, that everything starts from the protostar before it becomes a star. And what makes the difference? Nuclear fusion. So nuclear fusion is the reaction that takes place at the core. I don't want to get technical about this, but this is actually a process whereby hydrogen combines with another hydrogen to form helium together. So they join together, forming helium with neutrino, stream out, they pass through anything unreacted. So they form neutrinos, and then this enormous energy, which is what makes the star to shine. So that's what nuclear fission, right? And so, like I said earlier, today we're interested in stars that are bigger than 8 times, the size of the sun, right? So the condition I've said earlier, the core must be dense and hot enough for this nuclear fission to start. And I've said that the mass of the protostar will determine the mass of the star. Now, why did I choose to talk about massive stars? I mean, I would have decided to talk about the sun or the lower mass stars. So, but then massive stars are kind of interesting because they have more fuel, which means they have more mass, so they have more fuel. They burn really, really fast. They can be quite hot. And because they burn really fast, they use up their fuel fast. So they have a short lifetime. So it's easy for us to, study what is going on with a massive star because they have short lifespan. We can probably see their ending, but it's somehow difficult to do this for lower stars because they live long. So these are some of the motivations behind massive stars to study. And they are also dramatic, in the way they behave, as we'll be seeing shortly. Yeah, so these are some of the reasons, and I hope we get a thing or two from this. All right. Yeah, so just a bit of a recap and just to get us thinking. I don't know if anybody here likes coffee like me, but I think it would be interesting for people to type into the chat, what you have learned so far about massive stars. I know it's not a lot, but we just want to make sure that everybody is understanding. If you have any question, I will be happy to take them within this short time before we continue. So please type into the chat. Let's hear your thoughts. What do you think? What have you learned? Some of the things I've mentioned, does any of them sound weird to you? Yeah, so feel free to type into the chat and let's see.
All right. So we have actually quite a few questions for you, Adaeze. The first one is from Plazi in the YouTube chat. They said, I've always wondered, can stars be born from supernova clouds of dead stars or only from virgin clouds of gas?
Okay, thanks for that question. Right, so eventually the universe is cycling. It does what I would call a cycling. So that the materials that are released during a supernova eventually would move into space, join with other materials from probably other supernovas or things that are in the interstellar medium to form another big cloud. And that cloud over time, which is usually a long period of time, would eventually start collapsing under gravity. When it becomes so dense, it will start collapsing under gravity and begin to form another set of stars. So the answer to your question is yes. Yes, so we can form other stars from remnants of supernova. Yeah.
Awesome, thank you. Our next question is from Ward. The question is, when a star forms, what is the material that primarily makes up the core?
Good question. So I mentioned nuclear fusion earlier. So that is the reaction that takes place at the core. And for that to happen, you need to have hydrogen, a lot of them, because two hydrogens would combine to form helium. So this is a process that sustains the sun and so many other stars, at least for the first, million years, so that they bond hydrogen to hydrogen, forming helium. But they will get to a stage where they will start burning helium and form carbon, and then carbon will burn, form oxygen, and that's how many of the elements that we have today are actually created. So, but the basics for the core is hydrogen.
Awesome. And I believe we have one more question from Somerville in our YouTube chat. They're asking, what are the temperatures between massive stars and our sun?
Right. So the surface temperature for our sun right now is like 6,000 Kelvin. So, but for a massive star, we are looking at something in order of 10 to the power 6 Kelvin. I don't know if that makes sense, but that's a lot.
Yeah, that's quite a bit. And finally, our last question that we have for now is for nuclear fused atoms such as helium and etc. When fusion occurs, do the atoms migrate to the core or to the surface?
That's an interesting one. So as nuclear fusion is going on, so there are helium atoms produced, and so some of them will remain in the core. Of course, there are some migrations to the shell. So when I mean shell, some other layer above the core, right? Because eventually the shell would burn also. There is what we call shell burning. So this happens as well. Even when the core stop burning, at some point the shell will keep burning. So I don't know whether to call that migration, but definitely there would be materials in the shell that would come from the core due to nuclear fusion.
Alrighty, that's an excellent answer. And we don't see any answers in our YouTube chat for the quiz question, but feel free to answer in the chat should you have them, and Adaeze will be able to answer them for you.
Yep. I think I see some questions here. You said the disk of material around the protostar provides the materials for the formation of planets. What do we know about planets around massive stars? Yes, we know some planets around massive stars, and of course they are formed from the same materials. So I don't know where this question is getting at, but we know some planets around massive stars. They are not usually a lot, maybe one planet or two planets. But yeah, a lot of studies are going on discovering some of these exoplanets. So all the other planets that are not in our solar system are called exoplanets. And yes, a lot of them have been discovered. All right, I think we are going to move on. Thanks a lot for all the questions. Keep them coming. I'm happy to take them. And yeah. All right. So I want to introduce to you a popular star, the Vertical star. I hope so many people are already aware of this. So, but this is one of the stars that captivates us recently because it's not just a massive star, but is a dying massive star. So the image by the side is the Orion Nebula. So this star happens to, be close to the Orion Nebula. So we have this reddish thing that is on top. I hope you can see that, compared to other things. So now this is the Vertical star. So you notice that it's not bluish, like I mentioned. This is because it's on a phase where it's red. So this phase is what I'm about to talk about right now. So the Vertical star is no longer burning hydrogen in its core. So when it's burning hydrogen, we call it the main sequence state. But right now, it has moved to what we call this red supergiant. And so I will be talking about the red supergiant phase now. So massive stars, after burning hydrogen in their core, when hydrogen stops burning, then they get to this state called the red supergiant. And the red supergiant is usually more bigger. So what happened is that the hydrogen in the shell starts burning. And as it's burning, it kind of makes the envelope to be bigger. And that kind of cools down the star. So you see that the kind of light you see is red, more red. That's because the star is now cooler. It's not as hot. So it becomes cooler and becomes reddish. And it becomes bigger. So imagine that something expands. So as it's expanding, it cools down. So that's what forms the red supergiant. And so this is the case for the Vertical star. Recent observations of the red Vertical star have, figured out that it's kind of having some changes even in that stage. So in January 2019, astronomers were able to capture that using a telescope called the Sphere. It shows that in January 2019, it was kind of more bright, as you can see from this image, and the shape was kind of, spherical. But in December 2019, it's looking dimmer and kind of weird. So the sphericity is distorted, if you notice, in December 2019. So this is the kind of thing that happened in this stage. So there are a lot of variation going on. And by 2020 February, it has stopped dimming, it has stopped changing in variation, but then it's kind of brightening. So now this is the kind of thing that happens when a star is about to die. It undergoes a lot of variation and it undergoes a lot of mass loss. So what do I mean by mass loss? It releases a lot of its material to the surrounding. Yeah, it releases a lot of its material. This is one thing that we know about massive stars. So they shed their material towards the end of their life. And I'm suspecting that this is what Betelgeuse is doing right now. Yeah, we hope to, hear more about what's going on in this interesting star in the nearest future. All right, so let's look at the next phase. Cool. This is the most interesting part. I love this phase a lot, the supernova. So for a massive star, after the red supergiant, it's going to get to a point where the pressure is generating inside will no longer balance the gravity that is keeping it as a star. And at that point, it's going to lose its balance, it will collapse, and it's gonna explode. So it collapses into its core and then the core would explode. So that explosion is what we call the supernova. I like this a lot because we learn so many things using the supernova explosion. And I'll be discussing more of this. And I'm sure many of us are excited about supernova as well because it's an interesting explosion, in the universe. So the images here are different supernova explosions that have been captured using different telescopes at different times. So the first one, the SN 1987A, is one of the interesting supernova that was captured using different telescopes. Hubble, Chandra, a lot of telescopes actually captured this, and we are going to be looking at that later. But for now, it just needs for you to notice that there are different morphology of this supernova. So every star is unique and they explode in different ways. This is 2006 GY. You have the Cassiopeia A and the Crab Nebula. All of these are different explosions and they are all looking different, right? So, each of them are different. So we know about supernova because we monitor the sky every time. I will be discussing very soon how we know about these things. We'll learn the techniques that astronomers apply to get to this information. All right. So, but in the meantime, let's look at the next phase. So we have that after this explosion, the core remnant of the supernova could either be a neutron star or a black hole. So when these materials of the supernova are kind of thrown out, there is something remaining, the core, depending on, the technique, I don't know, whatever caused that explosion and the mass of the core remains. It could be that it's big enough to form a black hole. Sometimes it could be that the material was not thrown out, but then collapsed into the core and then didn't form a supernova explosion, but rather formed a black hole. So we are not sure exactly what leads to what, but we know that these two options could come from massive stars. So we want to look at the neutron star. Let's see what a neutron star is. So this is picture by the side is a typical neutron star that was inside a supernova explosion. So you have these clouds of material from the explosion, and at the very center, you notice if zoom in, you see this neutron star. So it's usually a very dense material, very small, but dense and highly magnetic. It's like 1.5 solar masses packed inside of Toronto. Imagine the size of the sun, then you multiply that, by half of it, and then put it inside Toronto. That's huge and dense. So this is what a neutron star is about. And it spins rapidly and emits beams of light. So for a neutron star that spins rapidly, emitting beams of light, we call it a pulsar. And so the beam of light crosses our line of sight, and we are able to pick these pulses. So scientists have been using this particular object, pulsar, to study a lot of things. So recently, we have seen the merging of two of these pulsars, which produced the gravitational wave, 3 years ago. And we are learning a lot through these things. Some of the theories that were given out by maybe Einstein or some of these, great scientists in the past, we are able to confirm them recently using this kind of object, pulsar. So it's an interesting object to look for. So, but we are going to look at the other part of it. So what if it wasn't a neutron star? So it could be a black hole. And this is another interesting object in the universe. So everybody wants to see a black hole, but then it's so shy to show itself. So we know that black holes are interesting, even though it's difficult to understand. So we have this image of M87. This is a black hole, in fact, the only one we have been able to observe. Now, when I mean observed, we did really see only the black hole. So what you see here, the lighted region, the lights in the event horizon of this black hole. The actual black hole is the dark region that is not emitting any light, because black holes don't emit any light. They absorb every other thing, but they don't give off light. So that's why it's difficult to really capture a black hole. So, but this was done using different telescopes in the universe. They kind of connected together using what we call very large arrays. So interferometry was connected, and everybody was looking at that object at the same time, and that's how we are able to get this image. So it's one of those very big achievements of astronomers, that were able to get eventually closest image of a black hole. So as we already know, it has a very strong gravity, and that makes it difficult for light to escape. So how are we able to learn about black holes? So we study things happening around event horizon. The event horizon is the boundary of a black hole. So beyond that boundary, everything is swallowed. So, but things happen. We see things happening, like sometimes we see a black hole swallowing a star. We see things happening, but we don't see the black hole itself, but we are able to see what's happening at the event horizon. And that's how we make all of these observations and predictions. We get all our information through, what's going on at the event horizon. All right. So I wish that we take some break. And in case you didn't like the coffee the other time, please take the tea, please, and try and put down names of things I've mentioned so far in the last couple of minutes into the chat. So let's see what people are taking away. Let's see what we are taking away. I would also want to take questions, and then I will play a very fun video for us to see at this point.
All right. Speaking of tea, some in the chat think M87 looks like a yummy space donut, nice and glazed. So that's got me a little bit hungry. We've got a few questions again. So one from Plazi again, and they are asking, what causes a gas cloud to form into binary stars as opposed to one giant star? So what creates that sort of separation?
Absolutely. So this is one of the puzzles we are yet to answer. What will be the condition for a cloud to form binary instead of a single star, right? So I know there are a couple of thoughts, but it's one of those things we are still trying to figure out. Yeah, but we know that there are binary star systems today. So different thoughts. Imagine the cloud, the cloud that is forming the star has very close spherical balls to it that are bounded by gravity, and they refuse to kind of separate. It's very possible for those to eventually become stars and then form a binary. That's one thought. Then there are other ways of forming binaries. Some binaries are not formed originally from birth. Some binaries are formed over time. So you have a star that has been a single star and then minding its business, and then maybe there was a supernova. Most times supernova kind of shift things. So they probably throw away their remnants, maybe a neutron star, and then it gets closer to a star that is close by, and before you know it, maybe it's within the gravitational influence of that star, and they could form a binary. So you see binary systems of star and neutron star, or star and a black hole, or star and what we call a white dwarf, which is also one of the objects from Low Master. So some binaries are from birth, some are not. And I don't know very well about what would lead to a binary, apart from what I've said already.
Alrighty, thank you. We got a few more questions. First one is, you talked about Betelgeuse dimming and brightening because it might be shedding its material. Are there other reasons the massive stars dim and brighten?
Right, so there are a couple of reasons that are maybe more technical. So there are things going on inside. So as the shell is burning, it's releasing materials, pushing things further out. As the things are being pushed further out, they expand and cool. So that's also a variability. So they expand and cool, they come back again and kind of expand. So there is what we call pulsation. So there is this, back and forth, cooling and contract and expansion that's happened because of the shell burning and what we call convention. So like I said, that might be more technical, but yes, even when it's not shedding material, though that pulsation could cause loss of material. So, but that's another thing that leads to the variability, the change in brightness. Yeah.
Great, thank you. Another one about supernovas. How bright is a supernova explosion? At what distance might this type of explosion be dangerous for us on Earth?
Interesting. So in some minutes time, we'll be digging into supernova, but just a quick one. A supernova explosion could be brighter than this host galaxy. That's how bright it is. Very bright. So, and they are obviously not so close. There are some close, but when I mean close, it will still take the light from the closest supernova at least 100 years to get to us. That's if there is even anyone that close that I know. So the ones we have been seeing are far away. And trust me, it's not going to affect anyone. Even the ones that we have seen is not affecting the star around because they are far apart. So even though the brightness becomes very, very, luminous, brighter than its host galaxy, that does not mean that it's affecting nearby stars. So do not worry about that. Supernovas, they are on their own, they're not gonna affect any of us. So please.
That's good. And finally, we have one more question for you in this round. Can we predict whether a massive star will become a neutron star or a black hole?
Interesting. I feel like all of us here are scientists and do need some of your thoughts. So this is something we are also thinking about. So we have been doing a lot of simulations trying to understand these things, to know what's causing this. So a lot of prescriptions are being applied to see what is causing neutron star or black hole. So the only thoughts for now, which have not been proven, of course, is that a black hole could be formed if this massive star that was supposed to explode end up collapsing into itself and not explode. Yeah, that's also possible. Now, depending on the mass that is remaining, remember, it loses a lot of material towards the end of its life before it explodes. So if it loses so much material that the mass remaining becomes so low, then it may not be able to form a black hole. Because black hole is actually dense, quite massive in terms of the weight, even though it might be small, but then it could be quite, massive and heavy. So you need a lot of mass to form a black hole. So if we don't have enough mass, then we probably can't form a black hole, at least the stellar black holes, because there are supermassive black holes that sit in the center of galaxies, which we are still trying to understand where they come from. But I'm talking about the stellar black holes for now. Yeah. So that's an option. And then, depending on the mass of the core remaining. So if the mass of the core is in terms of 8 to 25 solar mass, then it can form a neutron star. Then something beyond that could probably lead to a black hole. So that's what we are working on for now. But this is still something under consideration. A lot of work is going into this right now.
Great. Thank you for that. I don't think we have any answers in the chat based on your questions. But again, feel free to throw them in the chat as Adaeze speaks. I think everybody got their tea and their space donuts and they're ready for you to continue the next round.
That's cool. All right. So I would think at this point we should play the video. So I think it might be useful. Releasing a lot of material into its surrounding, and these materials are forming some circular things around. So it hasn't exploded yet, but it is exploding. So it's releasing a ton of material, and they are slowly moving in space. The materials are now is exploded. So you see the shock. And this shock kind of slam into those materials and brighten them as well. But then there is something remaining. As you can see, it left a core remnant. Okay. So that video was made by ALMA. ALMA is a very large telescope in somewhere. Yeah, I'm trying to remember the location right now, but it's one of those interferometry, radio interferometry that's looking at things using the sub-millimeter wavelength. So they put that artistic impression together to explain what's going on. So that video shows a dying massive star releasing a ton of material into its surrounding just before it exploded. And then you could see how the explosion produced a shock wave, and then that shock wave slammed into the circumstellar material that was released. And as it slammed into that, it kind of amplified the light. So this is one of the tools we use to understand massive stars. So we'll be going into more study on supernova. So first of all, if you have any question based on this video, please feel free to ask your question and I will get to them. So how do we know it's a supernova? Someone already asked me this question. So the image by the side is, a typical galaxy, and you see the very bright spot by the side. So imagine this galaxy and then imagine this bright sun. The sun is even much brighter than the galaxy itself. So this is what happens. So as we span through the entire night sky every time using a telescope, sometimes we see a very bright spot that weren't there before. So maybe something that was not there before, you have been looking at that location and all of a sudden you see this very bright spot. So that's how we know explosions occurred, and then we begin to look in details using other telescopes to see what kind of explosion. Is it a supernova, or is it a gamma ray burst, or a fast radio burst, or there are a lot of explosions these days. So for supernovas, they are incredibly bright. And so this is one of the ways we know that, oh, a supernova just went off. So we have different telescopes that are able to see the different colors of light emitted in a supernova. So the first one is the Pan-STAR. The Pan-STAR telescope is an optical telescope, and it's been doing a great job these days trying to get the different explosions, in the universe and a lot of other things. I use this for one of my research. One of the very luminous supernovas that I studied was observed and discovered using this telescope, the first one. Then we have the Chandra. I don't know if any of us have heard about the Chandra. It's actually a space telescope. Chandra is in space, is seeing things in the X-ray regime. So I think I should step back and try to enlighten us again on all these wavelengths of light. So electromagnetic waves have different wavelengths of light, which I call colors of light. So it has the X-ray, that's gamma ray, it has the ultraviolet, it has the visible light, that's the infrared, the microwave, radio wave. So radio wave are the ones that we use to transmit the phone calls, the DSTV, the Netflix, and even what we are doing right now. So we also get those waves naturally from objects in space. And so we have these telescopes that are able to see them. Right. So Chandra sees in the X-ray. Now, the one next to it, which sees an array of different telescopes, is the ALMA. The ALMA observatory is an interferometer. So interferometer is an array of different telescopes. So it's connected through fiber optic and is able to see things even much better, with much better resolution than a single dish would do. So the ALMA telescope is looking at things in the millimeter, and microwave regime. So these are telescopes that have been seeing a lot of supernovas, especially the ones I've been studying. And the one, just under the Pan-STAR telescope is I think this is the Gemini telescope, seeing things in the infrared and also in the optical. We have the one in the middle, which is also an array of radio telescope with the very large array, the VLA. So this telescope has been seeing a lot of explosions, like supernovas as well. Then the Hubble, everyone knows Hubble is the space telescope. It's very good for ultraviolet radiation because they don't get into air. Ultraviolet radiation don't pass through the Earth atmosphere, X-ray don't pass through the Earth atmosphere. So you need a space telescope to capture those ones. So, and that's why we have the space, the Hubble space and the Chandra. So yeah, and they have been very useful to us, as we'll be seeing in the next slide. So, what do scientists do? What do astronomers do? We do observations. We observe these things. We don't create them. So we observe them, try to understand them, propose theories to explain them. Now, we sometimes do some simulations, trying to understand what we see, and then go back to observation to confirm things. And this is how we make findings. This is how we make findings. Sometimes we start with theories and then do predictions and then observe. So for observation, we are able to use the different telescopes that I've mentioned to see things in different ways. For example, this particular supernova, SN 1987A, the first image you are seeing is the optical image, and then it was also seen using the ALMA in millimeter wavelength. So the diagram has different versions. You see the one down, millimeter ALMA. That's the image you see when you look at it in the millimeter wavelength. When you look at it in another wavelength in the visible, you are able to see a different thing altogether. This is Hubble. Hubble gave us this one. Then using the X-ray telescope, you also see something different. So Chandra was able to capture this. So now you see the different wavelengths gives us different information. And this is one of the interesting things about my research. So I combine different telescopes to look at different, to look at something in different ways. That's what. So looking at a particular source in different ways, and then I combine this information to understand what I'm looking at. So it's called multi-wavelength study. So this is what happened. So I'm going to explain a little bit. I'm going to explain a little bit of this. So imagine the video we just saw. So if that star happens to be at the explosion center, so this is one of those diagrams that we use to explain things. So if the explosion center was hosting the star initially before it exploded, so you have the shock release, and then it moved out toward into space. And this shock, as the shock is released, the materials are also ejected. And so these materials that are ejected would slam the materials also around that were released by that star that was exploded, maybe some years before it actually, got exploded. And here we have the gray region. Those are different materials that were released by the star before it exploded. So I call that the circumstellar material. So now the interaction of this light produce different kind of light. So you have the black body emission, which is seen in the optical. We are able to see this, at the shock front. where the explosion happened. So we see things using optical telescope. So the optical telescope will be showing you what happened at the early time during the explosion. While we have things moving further out and then forming some radio wave because of synchrotron emission. These are different techniques that produces these kind of radiations. You don't need to worry so much about them, but just know that different techniques produce the different wavelength light that we see. And they are kind of created at different locations. So when you see those lights, you are able to interpret what's going on at those locations. So to make it more clear, the plot here is showing the circumstellar density and the radius, which can also be called the time after the explosion. So you see that early times can be seen using the optical telescope. So the things we learn from optical telescope would explain what happened early time before the explosion. While later time, so after the supernova had cooled down, maybe after 3 years or more, we'll be able to have the light reaching out to materials that were thrown out even much later in the life of that star before it exploded. So as light gets more into space, we are able to see in the radio. And the things we see in the radio turn out to give us information about what happened in the very past of that star. I'm going to take it down. I'm going to slow down. Okay, now look at this other plot. This is time of mass loss pre-explosion. It's actually another way of explaining the radius. So that going backwards, so you learn things backward. As we are studying the supernova, we learn about what happened in that star before it exploded. So we kind of go back in time when we studied the explosion and the material that were released. Okay, so we have, some of the techniques. I may not go into detail, but we have some radioactive decay going on, which is powering the explosion itself. The radioactive decay, which is also producing the heavy element, some of the heavy elements. And then we have the materials that were released also powering that, very bright light that we see. So just in case if you're thinking of what could be, the power source of those supernovas. So we have the radioactive decay of nickel, and then there is the dense material. If light slam into that dense material, it amplifies it and you see the brightness increased. There are other techniques, there are other power sources that I didn't include here, like the magnetar case, whereby if a neutron star was formed, at remnants, it's going to spin and cause much more higher luminosity of that explosion. So there are different power sources, but I kind of like this too. So that's why I'm showing you. These are the two that I'm really, really working on. So now this plot by the side by Smith, 2016, this is one of the astronomers working in this kind of thing. There are different, mass loss and then expansion velocity that have been found for different explosions. And so when we study this thing, we are able to, measure the mass loss. We can tell a lot of information. We can give a lot of information about the star that just exploded from just studying the supernova itself. And so when we find these values, we come to this plot and cross-match things. You discover the kind of star that got exploded just by taking those values and coming to this table, these plots, rather to look at where the value kind of lies. And so through this technique, we have been able to learn a lot of things. We have discovered so many stars that exploded. So because sometimes we are not able to see the star when it was alive, because our lifetime is so short compared to the lifetime of stars. So we learn about them through their explosion. So that's like going back in time. Again, I'm gonna slow it down. So take a deep breath. I know this sounds like a lot. I'm happy to take questions. So when we combine observations with theories and using these techniques, what do we learn? So from the explosion, we learn the nature of the materials shedded by the mass few years before the explosion. So we learn about the material that was shedded few years before the explosion. How do we know this? We are able to use optical telescope to see them because they are emitting in the optical. We are able to see them using ultraviolet. We are able to also see the dust using infrared. And then we learn about the velocity with which it was released, or with which it's moving into space after it was released. We learn that using the radio. The radio wavelength gives us this information. And then the mass of the material that were thrown away can also be calculated. And that helps us even know the mass of the star. By the time we add up the mass of the material thrown away, we add up the mass of the remnant, we are able to add up and know the entire mass of that star initially. And that's how we know, okay, it's a massive star that just got exploded and all of that. So we learn this using the X-ray and the radio. So the behavior of the star prior to the explosion, we learn this as well, like the mass loss, the cause of the explosion, the cause of the mass loss. So this is very good for late time stages of the life of that star. So this has been a challenge for astronomers, understanding the late time stages, what is actually causing the supernova. So this is an area of active research. So maybe in the future we could learn more things and update everyone on what's going on. Okay, I think at this point, we can wrap it up with putting into the chat what you remember after today. What would you remember about supernova after today? And then I'm happy to take a lot of your questions at this point. Thank you once again for listening to me. I hope some of this makes sense. I'm not expecting that all of them will. But yeah, let's hear your thoughts. Let's hear your questions. Thank you very much.
Thank you so much, Adaeze. We are going to check in with our outreach coordinator, Shaheen Dashkian, one last time for any final questions from our YouTube audience. Shaheen?
Thanks, Denise. We certainly have quite a few questions to wrap it up. First one again, coming from Plazi, and they ask, are new elements created when the shockwave hits the outer cloud?
Great question. So there are new elements produced during the explosion itself. So there are some produced at the core, some produced at the envelope when the shell are burning. Then during the explosion itself, some are produced when the material are slamming the things in the CSM. I don't think, well, I would say that I'm not sure if things are produced when they are slamming the CSM, because mostly what happens is that the CSM is amplified, like the lightning, they're amplified. There are some processes that go on that produce radiation. So that is what we call synchrotron processes. These things go on when when this material is slamming, and there is also blackboard radiation process going on as well, producing the different radiations. So I'm not sure if new elements are created at that point. I'm sorry. Pardon.
We have another question from S. Somerville that kind of hits close to home for us at the DDO. They would like to know, don't the thousands of satellites in orbit around Earth affect viewing quality of telescopes on Earth?
Oh, no, no. So remember that the Earth is big on its own, and the satellites are placed at different orbits. And the way they are placed are kind of monitored in such a way that, they don't interfere with each other. Definitely, we get some radio emissions from them, which we have a way of removing in form of noise, right? We have a way of removing this noise. But it's not just about satellites. Even phones we use are contributing to the noise we have in the telescope when we do operations. So we kind of have a way of subtracting them off, but not quite intense, coming from this satellites. No, no.
Okay. Thank you for that. Another one from Plazi. What causes the pearl bracelet shape of SN 1987 day?
Right. Don't know either. So that's because that was what the telescope captured. Maybe a more detailed, maybe they have already figured it out. So let me take us back there. This is the particular one I'm talking about. Yeah, so this is, like I said, different wavelengths will give you different information. So, these different wavelengths, like this one in particular, I can tell you that the ring region could be the point of, the shock front, and the shock front kind of slamming into the CSM and causing those amplifications that I talked about and some other reactions going on. That's because that region, we get optical emission from there. And so it's very possible that that's what we are seeing right now. There are also radio emissions from there. So I think that's what's going on there. Yeah.
Yeah.
So these things are different for different explosions, depending on each one. They're kind of different.
Okay, thank you for that. One more we have. So this one says, apart from Betelgeuse, are there any stars we, the non-expert viewers, might know about or be able to observe that we should be keeping an eye on as candidates for supernova explosions?
Right. So right now, they are far away. The ones that they are not things you can see with your naked eye for now. Yes, but there are some you could see with telescope that people are monitoring right now, waiting for when they would explode. So apart from Betelgeuse, there's no one for now that you could see with your naked eye.
Lovely. And we have one final question for you. This is a really good one. In recent months, one of the issues we have been discussing in recent months is improving representation for minority groups like people of color and women in astronomy. Can you please tell us a bit about the challenges you might have faced in getting into astronomy as a career? What would you suggest for young people from underrepresented groups who aspire to become astronomers?
Wow, that's an interesting one.
Yeah.
Yeah, I get a lot of this question though, especially because of my color, I guess. So I think we are all aware of the recent improvements in the last couple of months. I think there are a lot of developments in terms of inclusion. So different institutions are working hard to see that their EDI bottom are checked. But then I guess there are more to be done. So last week I was in a panel discussion and we were talking about it as well. So the only advice I would give to someone coming from minority side like me is to come with an open mind. On your own, you want to understand the system. You want to be inclusive yourself. You want to understand that everyone deserves, equal rights. So you yourself has to be inclusive. You yourself have to be inclusive in your behavior, in the way you talk, and with the way you meet with people and everything around about it. And then be your best the much you can be. And I believe that when you are at your best, it's hard for for you to be discriminated. It's hard. But even now, I'm kind of optimistic that things will be better because of the awareness that is going on right now. So I think it might be easier for the future generation with the way I see things. I mean, there are some improvements going on here and there. So I would say keep it optimistic and, be at your best. You yourself, be inclusive, you know. I know it's a lot. It can be challenging. It's sometimes you want to work as twice as you are supposed to, just to make sure that you are matching the standard and everything. But I think that's that's the best you can do because you can't force yourself on anyone. We are only hoping that, we'll get to that point where the environment we find ourselves will be inclusive in general. Yeah. I think that's what I have to say on that.
Awesome. That's a great answer. And so I have one final question myself. How can our viewers at home watching tonight and later on keep up with your work, get in touch with you, ask you any questions?
Right. So I think you can post my Twitter handle on the YouTube channel and feel free to tag me and ask questions. And then yeah, I think Twitter is good. Ask me your questions and I'll be happy to reach back. There are other resources that I've given out for people. I don't know if you have posted them. Those are also helpful with understanding some of the things we talked about today. And it's also for kids, especially for kids. So please feel free to reach out and I'm happy to answer your questions.
Okay, thank you very much for that.
Thank you.
Thank you, Shaheen, for relaying all of these questions. And thank you so much, Adaeze, for taking the time to answer the questions and for sharing all the resources that you've shared with us.